Good afternoon, everyone, and I would like to welcome you all to the first of the student seminar series. We have here with us Amoghavarsha from MAC Physics second year. A quick introduction about Amogha. He got into physics. He got into physics because of his interest in astrophysics and astronomy, and he decided. Good afternoon, everyone, and I would like to welcome you all. Oh, sorry, first of the student seminar. Yeah, sorry. Right. So as I was saying, Amogha got into physics because of his interest in astrophysics and astronomy. And in high school, he decided that it'll be easier for him to pursue physics because that's the only subject which apparently didn't require memorizing. And it's been working really well for him. And to this day, his journey has been wonderful. He has different kinds of experiences as an intern, a winter school student, for kids, a volunteer, and so on and so forth. Currently, Amoghavarsha is also a visiting student at the Indian Institute of Astrophysics in Bangalore. And he is always enthusiastic about physics. And without further ado, I'd like to welcome Amogha here for the first of the seminar uh, on the topic Odyssey of Classical Mechanics. Amogha, this floor is yours. Go ahead.
Hello, good afternoon, everyone. I I don't think I need not to introduce myself as Vikrant has already done it. I think it's my pleasure and privilege to kickstart this student seminar series. And since this is the first of its series, so I have not made it too much mathematical, and I have kept it very simple. Okay, so let's start with the timeline of classical mechanics. Hope I'm audible and my audio is good.
Yes, you can go ahead.
Okay, so the timeline of classical mechanics starts in the 4th century BC of the Aristotle. Yeah, uh, the 4th century BC with the Aristotle. Aristotle invents the system of Aristotelian physics, which is later largely disproved because of his assumptions and so on. And at the same time, Babylonian astronomers calculated Jupiter's position using the mean speed theorem. This is somewhat more scientific compared to what Aristotle did, is what I would say. In 260 BC, Archimedes works out the principle of the lever and connects buoyancy to weight. I have some videos to show in this talk where we'll be discussing Archimedes principle. Okay, then in 6th BC, hero of Alexandria writes Metrica Mechanics on means on those days there were heavy concentration on the regular day stuff, means how to lift objects, how to transport it to one place to another place with ease, and all of that. And people were thinking and doing some calculations regarding that. And Hero of Alexandria was one among them. He has written many things regarding the same, and also pneumatics, which is nothing but machines working on pressure. And I kind of quickly jump to 14th century. This is just a abstract kind of thing, so I'll go in detail later. I'm coming to 14th century, where Oxford calculators and French collaborators prove the mean speed theorem of, if not very elegantly, but yes, they do it kind of more mathematically compared to the previous non-mathematical treatments. And then in 1500s, Al-Birjandi develops the theory of circular inertia to explain Earth's rotation. And the major one happens in 1581 when Galileo Galilei notices the timekeeping property of the pendulum. We know the common relation of 2 pi root L by G, but yeah, that is developed afterwards. And in 1589, Galileo uses balls rolling on inclined planes to show that different weights fall with the same acceleration. You might have seen the picture of Galileo Galilei holding a uh, inclined planes with small pebbles kind of thing. That's a famous picture. But we'll be seeing the another famous Eiffel Tower, Pisa Tower experiment in this. Okay, in 1658, Christian Huygens experimentally discovers the balls placed anywhere inside an inverted cycloid reach the lowest point of the cycloid in the same time, and thereby experimentally shows that the cycloid is a protochrome. You might have seen uh, in amusement parks where the roller coaster goes and makes a turn and doesn't fall back. This is kind of that. And 1677, Spinoza puts forward a primitive notion of Newton's first law, even before Newton's, but not mathematically. In 1687, Isaac Newton publishes his Philosophiae Naturalis Principia Mathematica, in which he formulates Newton's laws of motion and Newton's law of universal gravitation. In 1690, James Bernoulli shows that the cycloid is the solution to the tautochron problem, which we discussed here. And in 1733, Daniel Bernoulli derives the fundamental frequency and harmonics of a hanging chain by solving an ordinary differential equation, which is quite surprising at that time, is what I read. And you should also note the difference between many Bernoullis coming. As I said, in 1690 it was James Bernoulli, and in 1733 it was Daniel Bernoulli. If I remember correctly, there was one more person with his last name Bernoulli. So yeah, in 1749, Euler derives equation for Coriolis acceleration. In 1788, Joseph Louis Lagrange presents Lagrange's equation of motion in the Mechanic Analytic. This was what he published in 1788. And in 1821, William Hamilton begins his analysis of Hamilton's characteristics function and Hamilton-Jacobi equation. And yeah, I'm sure the first year students will be learning this by answer, and also might have learned in the UG as well. And the major remarkable one happens in 1915 when Emmy Noether proves Noether's theorem, from which conservation laws are deduced. Uh, yes, so now we can have a look at the timeline. It starts with Newton, uh, excluding all those B.C.E. era. It starts with Newton calculus, 1670. Along with Newton, Leibniz also simultaneously works on calculus, and that is mathematical part of that. Here we can see Newtonian mechanics, gravitation, that leads to equations of motion, and there's applications mentioned there. And if we come to calculus, then the calculus develops into calculus of variations, then D'Alembert's principle in 1743. Then, as I mentioned earlier, Lagrange introduces Lagrangian mechanics, and Hamilton improvises it, and it becomes Hamilton. And also using Hamilton's principle, we get to have Hamiltonian mechanics. We know that both Lagrangian and Hamiltonian mechanics are used to obtain the equations of motion. Then Jacobi comes into picture, and he develops much more advanced theory called Hamilton-Jacobi theory that is also used to obtain the equations of motion. From this point, we have further branching, as mentioned here, statistical mechanics, relativistic mechanics, and quantum mechanics. All these other branches came out of kind of mechanics. So I'll not go into the details of the historical developments of either statistical mechanics or not quantum mechanics, or not even relativistic mechanics in this. So yeah, let me introduce briefly what classical mechanics is. It's a physical theory describing the motion of the everyday life, means the objects that we see every day, from projectiles of parts of machinery to even astronomical objects such as spacecrafts, planets, stars, galaxies, and even when you throw a ball, you can calculate the range, height, etc. So it's the physics that's used in everyday life. To be precise, okay, the earliest development of classical mechanics is often referred to as Newtonian mechanics because Isaac Newton was the one who kind of give humongous, means a very large contribution to the mathematical development of mechanics, and the classical mechanics kind of almost relies upon the Newton's frameworks and what he did. The mathematical methods were invented by Leibniz, Joseph Lagrange, Euler, and other contemporaries in the 17th century. Is also used to describe the motions of bodies under the influence of system of forces, means, and also mention constraints. These are a kind of alternative paths when the application of Newton's laws of motion becomes difficult to apply on a system and to get the equations of motion. So classical mechanics provides extremely accurate results when studying large objects that are not extremely massive, and the speed is not comparable to that of light. Means C. Although it's the oldest branch of physics, the term classical mechanics is relatively new. I'll get to that in a few minutes. Uh, the equations developed prior to 1900 were still perfectly suitable for describing objects of everyday sizes and speeds that I have already mentioned. The term classical mechanics was coined to loosely label the set of equations, means to differentiate between the quantum and relativistic mechanics, where the velocity is very much less than c, and also in a inertial for Newton's laws to be obeyed. So yeah, mechanics kind of later became classical mechanics, and we attached the word classical in the beginning of 20th century, to be precise. Classical mechanics is the oldest branch of physics and basis for all other areas. That's why we need to learn classical mechanics, even though we have advanced in many areas, and but once, okay, I can see someone raising hand. Yes. Do you have any question? Hello. Hello.
Hey, Prabhu, do you have a question?
Okay, let me move on.
Yeah, please go ahead.
Yeah.
If there are any questions that go unaddressed, you can perhaps put them in the chat box.
Yeah, I think. Yeah, and as I said, it's the basis of means to study and understand electromagnetism, electrodynamics, statistical mechanics, relativity, and quantum mechanics. You need to have your basics right, means which is classical mechanics, and you need to learn it well. And it is largely a mathematical development of the Galilean Newtonian principles combined with the ideas of symmetry and group structure. And classical mechanics has very rich formal structure developed in stages over more than 2 centuries. Formally means the things that we study here in the college and stuff. Okay, so this pictorial frame means everybody uses it, and it's available on Wikipedia also. Just to put the speed, size, and the domains. Classical mechanics where waves very much less than c, and also the sizes far more than 10 power 9 minus 9 meter means very less than very much greater than, sorry, very much greater than nanometer scale. So you can say this classification. So if your size and velocity both is in this direction, you will end up in quantum field theory, which I'm not going in detail any of it except the classical mechanics. So here's one more classification where mechanics is in general divided into how systems means where and how do we analyze it. If it's mechanics of fixed or moving system of internal external systems like that. I think you can have a look for a second, then I'll move on. Yeah, there's also classical thermodynamics, statistical thermodynamics, and statistical mechanics, which arises naturally from the classical mechanics and which doesn't require, uh, let's say, a quantum mechanical interpretation. We have fields called classical thermodynamics and classical statistical mechanics. Okay, so I'll move on. So now we'll come to the timeline from ancient times, how people were thinking of objects or how people were thinking of mass, weight, all those things. The, the ancient civilization of Mesopotamia, Egypt, and Indus Valley all demonstrated an understanding of the motion of sun, moon, and the stars. And also, let me mention you in this point that in the ancient times, the laws of physics on terrestrial surface, means on Earth, were assumed to be different from the laws of physics in the heaven. Means they used heaven to describe sky and the stars. So they thought different kind of mechanism works separately in heaven, I mean sky and stars, and on Earth. And we are still at this point of time, and we have, I mean, our frame is restricted in this. Okay, so celestial mechanics thusly became the study of how things move about the heavens, and the ancient Greeks were the first to consistently link natural. Means you might know about the Greek mythology and all, where the stars and the planets are assigned to and attributed to some gods with some supernatural powers. So some of the Greeks uh, thought of expediting and understanding of the celestial bodies with a scientific approach. Means natural approach is meant a scientific approach. So philosophers like Thales in 1624 BC rejected non-naturalistic explanations for natural phenomena and proclaimed that every event had a natural cause. Means he was a philosopher who thought no, there's not a super magic or something is going on. Everything happens because of natural cause. Is just what he said. Means at that time, a particularly tenacious set of wrong ideas centered on motion, which for nearly 2000 years built on the work of Aristotle. That the theory of impetus. I'm not sure whether how many of you heard of theory of impetus. Even though Aristotle introduced his laws and his way of thinking, his philosophy 2000 years ago, it was still undergoing some, what shall I, revised edition kind of thing. And people were thinking based on what Aristotle told. So I don't, yeah, and it got major revisions since even in 6th, 12th, and 14th centuries, which is actually quite surprising. Means Aristotle kind of lived through his philosophies for about 2000 years without anyone objecting it, but rather revising and seeking much more details of what he said. So terrestrial mechanics is what the study of things that go on Earth's surface. So yeah, I think there should be a video here. Oh, One sec. Uh, yeah, I think this one. Okay. Oh, yeah. Just give me a minute. I think my laptop got disconnected from the college internet. Just a second.
So by the time he comes back, perhaps if there are any questions, you can unmute yourself now and ask them away.
Yeah, I think. Hmm. Oh, mm, yeah. Okay. I think I'll play this video afterwards. It's not. It was working fine, but it's, yeah. There's some issue with this. That's okay. I'll try to show those videos at the end. Okay, now we'll move on to the theory of impetus. Means this was the thought that happened in the medieval period, majorly in Europe. They introduced something called impetus, a physical quantity, which is weight times velocity. So if you do the dimensional analysis, or if you just substitute weight is equal to mg and mgv, which is not normally used in any of our equations, they use this kind of concept to describe the physical phenomena. The theory of impetus is kind of developed based on the principles of what Aristotle told. And it's also called a secondary theory of Aristotelian dynamics. Uh, and to explain the projectile motion, when some objects are under the influence of gravity. So it is the intellectual precursor to the concept of inertia, momentum, and acceleration in classical mechanics. I agree that they did mistakes, but these were the mistakes that made others to think why and how things move under the influence of gravity. So it was introduced by John Philoponus in the 6th century and elaborated by ad-Din al-Bitruji at the end of 12th century. As I mentioned earlier, Aristotelian principles got revised in both 6th, 12th, and 14th centuries. So there are many versions to this theory of impetus. One is Philoponine theory and Arabic theory and Buradinus impetus. Concept of conatus was also derived from theory of impetus. Means as an that innate inclination of a thing to continue to exist and enhance itself, just like perpetual motion or something like that, was also derived from theory of impetus. But there's no proof. There was no proof given for that, and it's baseless, as we know. Yeah, I had one more video. Yes, now it's working. I think. Is the video coming?
There once was a fellow named Archimedes. He was born in 287 BC in the city of
Okay. Yes.
Syracuse in Sicily. He was a Greek mathematician, physicist, engineer, inventor, and astronomer. One day, Archimedes was summoned by the king of Sicily to investigate if he had been cheated by a goldsmith. The king said he had given a goldsmith the exact amount of gold needed to make a crown. However, when the crown was ready, the king suspected that the goldsmith cheated and slipped some silver into the crown, keeping some of the gold for himself. The king asked Archimedes to solve the problem, but there was a catch. He couldn't do any damage to the crown. One day, While taking his bath, Archimedes noticed that the water level in the bathtub rose and overflowed as he immersed himself into the tub. He suddenly realized that how much water was displaced depended on how much of his body was immersed. This discovery excited him so much that he jumped out of the tub and ran through the streets naked, shouting, "Eureka!" which comes from the ancient Greek meaning, "I've found it!" What did he find? Well, he found a way to solve the king's problem. You see, Archimedes needed to check the crown's density to see if it was the same as the density of pure gold. Density is a measure of an object's mass divided by its volume. Pure gold is very dense, while silver is less dense. So if there was silver in the crown, it would be less dense than if it were made of pure gold. But no matter what it was made of, the crown would be the same shape, which means the same volume. So if Archimedes could measure the mass of the crown first and then measure its volume, he could find out how dense it was. But it is not easy to measure a crown's volume. It has an irregular shape that's different from a simple box or ball. You can't measure its sides and multiply like you might for other shapes. The solution, Archimedes realized, was to give the crown a bath. By placing it in water and seeing how much water was displaced, he could measure the volume. Then he'd calculate the density of the crown. If the crown was less dense than pure gold, then the goldsmith most definitely cheated the king. When Archimedes went back to the king and did his test, the story says, he found that the goldsmith had indeed cheated the king and slipped some silver in. These days, using the way an object displaces water to measure volume is called Archimedes' principle. The next time you take a bath, you can see Archimedes' principle in action. And maybe you'll have a genius idea of your own.
Okay, that was the Archimedes principle, which happened before Christ's era. And also I wanted to show the Aristotle's experiment. Let me see how this will work. Get loaded or not. I don't know. Yeah.
Aristotle. Born in 384 BC in ancient Greece, he was a famous philosopher. He also made great contributions to many other fields, such as ethics, politics, and science. One of Aristotle's most famous contributions to science is actually based upon a false claim. For years, Aristotle preached that heavy objects fall faster than lighter objects, stating that the speed at which something falls actually depends on its weight. He would explain it to anyone that would listen. His example was that an object 10 times heavier than another would have to fall 10 times faster. No one disagreed with Aristotle. Most people were comfortable with the idea of heavy objects falling faster because it's what they were used to seeing. For almost
I think this gives the idea of what Aristotle was doing in his principle. Let me go to the next slide because I think I can see some hands raised. If you have questions, please you can unmute yourself. Okay. Yeah, now one person. Go ahead if you want to ask some question. Yes, please. Okay, then I'll move on. Now we'll come to the Renaissance period. 16th century, the scholars began to notice that theory of impetus was ill-suited for describing many phenomena. According to the theory, a projectile should fly through the air until it runs out of impetus. It's like having some energy kind of thing is what they thought. Whereupon it should fall straight to the ground. In reality, the path of projectile is very specific. Means if you throw some stone, it will not go in a straight line till the impetus exhaust is what is the underlying principle. Okay, so in 1638, Galileo Galilei published the first mathematical proof that uniform acceleration would cause projectiles to move in parabolic trajectories that match observations, thus showing that the terrestrial mechanics are governed by mathematics. So this was the first experimental proof and also the first basis where the terrestrial mechanics were found to be agreed with the mathematics. Then and also we shouldn't forget Tycho Brahe was one of the first astronomers to use clocks, capable of counting minutes and seconds, along with the quadrants and sextants. At that time, think of 1546, to track the movements of celestial objects. And then in around 1600, we have Kepler, who based his three laws of planetary motion based on Tycho Brahe's years of experimental data of the motion for the stars. The Renaissance was not only kind of Renaissance happened with the arts or other field, it also happened with science in the Europe. Okay, let me, yeah. Now we'll have a look at Galileo's experiment. I think Arun sir might have uh, asked this you juniors and also some of us uh, on whether two objects having different masses left from the same point
In the year
reaches.
In the year 1589, an Italian scientist named Galileo attempted to prove Aristotle wrong. Galileo believed the only reason heavy objects fall faster is because air resistance slows down lighter objects, and that if air resistance could be reduced, they would both fall at the same speed. In order to prove his point, he gathered everyone in the city, climbed to the top of the Leaning Tower of Pisa, and explained that the only way to prove who was right for sure was to perform a scientific experiment. Galileo's experiment went like this. He stood at the top of the Leaning Tower and held out a cannonball and a wooden ball of the same size. The only difference between the two objects was their weight. Galileo explained that since they are the same size and shape, they would feel the same amount of air resistance as they fell. His conclusion was that they should hit the ground at the same time. So he leaned out over the edge, dropped both objects, and a little more than 3 seconds later, everyone in the city of Pisa saw the cannonball and the wooden ball land at the same time, proving once and for all that if there is no air resistance, all objects, no matter how heavy, will fall at the same rate.
Yeah, that was Galileo Galilei explaining his experiment and disproving Aristotle. So now we come to a major unification. As I told, some mathematics were developed to explain terrestrial mechanics, and some mathematics were developed to explain the mathematics of heaven. So now we have the golden unification of both heaven and earth. Adopting Copernicus' heliocentric hypothesis, Galileo believed that Earth was the same as other planets. Newton built on the work of Galileo and Kepler to show that the elliptical movements of the celestial realm and parabolic movements of the terrestrial realm could be explained by one mathematical law, and that is universal law of gravitation. This is where he kind of unified both terrestrial and the celestial mechanics. So Newton formalized the laws of motion by describing them in the language of mathematics, and this is something important. Euler extended Newton's laws of motion from particles to rigid bodies with two additional laws. Leibniz, as I mentioned earlier, who independently worked of Newton, developed a calculus with the notation of the derivative and the integral, which are used to this day. Means the calculus which Newton developed was slightly different in notation, but what we use is developed by Leibniz. This is a famous picture that you can find in any astronomy books, and this is by an unknown artist. Okay, just put it so that to support this concept of unification of heaven and earth, and by breaking all the barriers of what the ancient people had thought. So before Newton, earth had earthly things going on, and the heaven had heavenly things going on. Newton was the one who kind of combined both earth and heavenly things. So Newton kind of breached the philosophical barrier of great philosophers at that time, which some couldn't digest. In even both Copernicus, Galileo had some serious resistance from that time of the uh, church and also some philosophers of Europe. So classical mechanics grew throughout the 18th and 19th centuries to describe everything from optics, fluids, heat to pressure, the classical thermodynamics, electricity, magnetism. And I have a point uh, for you people to think. So I'll not go into much of Newton's work because it's all you people are studying from high school. His man of the millennium and his contribution is widely recognized in various ways. And also, one thing is uh, of interest is of thought process that he did was during the Great Plague of 1665, where he isolated himself in a farm for 2 years and came out with some very good results. So, yeah, he also had some good optics experiments in his farm. And this is Newton's own copy of his Principia with handwritten corrections for the second edition in the Brent Library at Trinity College, Cambridge. If you get a chance to go to Cambridge and Trinity College, please have a look at this. And now we come to Newton's laws of motion. Uh, I have stated Newton's laws of motion in the as it is in the Principia, and you can notice the difference between the regular form which we use and the original laws. This is from the Principia. I'll only quote the first sentence. Absolute space in its own nature, without relation to anything external, remains always similar and immovable. And then he lays down all these three laws of motion in his words. And for comparison, I have quoted uh, these three laws from some of it. Uh, you can have a look at it. And these laws are valid in a special class of frames of reference called inertial frames. If it is accelerating frames, then we know that the Galilean transformations won't work out, and we have to work the equations of motion in the accelerated frame, where we see Coriolis force and other forces, pseudo forces, come into effect. Okay, so compared to a frame fixed on Earth's surface, a frame fixed in a non-rotating Earth is better. Means if we have a inertial frame fixed at the sun, we'll get to have a better precision and accuracy. If we and also similar way we can do a transformation to the center of our galaxy to achieve much more precision. So this is some I thought might be of little interest. So now I come to the Lagrangian formulation, where solving equations of motions for a subject for system that is subjected to external constraints. The constraints are of majorly two kinds. One is holonomic and other is non-holonomic. I'm sure that you people will be learning all this in your first semester, the first year, guys, and second years we have already learned it. I hope you guys remember it well. And another type of classification we do is heteronomic and rheonomic, dependent of time and independent of time. Just to give an example, you can think of an oscillating pendulum with fixed length, which will give independent time, and a spring pendulum which varies its length with time. So we invoke the concept of a generalized coordinate, generalized velocities, virtual work, generalized momentum, and D'Alembert's principle. The Lagrangian L is T minus V, where T is kinetic energy and V is potential energy. And I have just mentioned the Euler-Lagrange equation in this slide. So now we move on to the Hamiltonian mechanics. It's a better version of Lagrangian mechanics. It's actually a reformulation in 1883, where instead of generalized velocity, we use generalized momentum. And Hamiltonian is the total energy of the system, but is kinetic energy increase the potential energy. Hamiltonian mechanics has a close relationship with geometry, symplectic geometry, and Poisson structures and all. I have just mentioned the equation just to have a look at. And we come to Hamilton-Jacobi theory. It was named after William Rowan Hamilton and Carl Gustav Jacob-Jacobi. It's an alternative formulation to classical mechanics. As I showed it in the first few slides, these are all the methods to obtain the equations of motion. So Hamilton-Jacobi equation is considered the closest approaches of classical mechanics to quantum mechanics. And this is the only formulation of mechanics in which the motion of particle can be represented as a wave. Even the Schrodinger equation, if you write Schrodinger's equation, we get something of this wave concept. This is something different from that. Okay, so yeah, I'll move on. This is just Hamilton's principal function, and moving from one Hamiltonian to another Hamiltonian. If you refer Goldstein, he makes use of this word called Hamiltonian. He uses K for this notation, and I'm sure you'll read upon it. Okay, so I'll move on something more exciting, I think. Yeah, Birkestock curve. It's one of the elegant and interesting topic in classical mechanics, and we get to know that the shortest distance between point A to point B is not a straight line but a curved path. Just forward it. Yeah. We have a device to measure the time where the ball reaches the point, and we use the concept of Birkestock curve, and we are leaving all the three balls together. Yes. And you can see the ball which has got the it's in the middle comes fast, and that is called Birkestock curve. You can also see the time. Now this is something important. Yeah, even the balls are released from different positions. The one with Birkestock curve reaches fast, and it's the curve of fastest descent. I will not go to the details of this, but this is historically has got many importance, and it was initially proposed by Johann Bernoulli, but the statement is given here. Johann and his brother Jacob Bernoulli derived the same solution. Interestingly, Johann's derivation was incorrect, but he took his brother's proof and solution and passed it to solution, claiming that's his own solution. So Bernoulli allowed 6 months time for people to verify, and if they have got some kind of questions, or if they are not agreeing with it, they could come and argue with him. But on the request of Leibniz, he extended it to a year. So at 4 p.m. on 29th January of 1697, when he arrived from home, this was Newton who found this challenge from Johann Bernoulli. So Newton stayed up all night and solved it and mailed it the solution anonymously by the next post to Johann Bernoulli. And Bernoulli, who knew that Newton would reply, made a remark that he recognizes a lion from his claw mark, because Newton's notation and his approach to solving equations were something remarkable and extraordinary. And something here I'd like to mention that Newton also wrote, "I do not love to be dunned and teased by foreigners about mathematical things," because Newton was from another country and Bernoulli was another country, but means they were from both different countries. Interestingly, Jacob, who was kind of anguished by this, developed new methods that his brother kind of acclaimed. His result has means he took his results. He developed new methods that were refined by Euler, and later it was refined by Euler, that led to calculus of variations. So I thought of showing Foucault's pendulum, that, but I'll not do that since I'm running out of time. It was, yeah, but you must read about Foucault's pendulum. I'll not go into this because I don't have time. I'll just say a few words about Noether's theorem. Noether's theorem primarily concerns the relationship between invariances and conservation laws. And she was the female mathematician and physicist, kind of, if I may say so, who kind of did a remarkable job in this aspect. She was a German, and she made important contributions to abstract algebra. Noether's theorem is used in very much in theoretical physics and calculus of variation. Okay, so you can read about Noether and Noether's theorem much. And I would like to mention the recent developments in classical mechanics. I have mentioned the topics, which I'll not read through, but you can go and search. This was the recent publication that I found in 2021, the generalization of periodic orbit dividing surface in Hamiltonian systems with 3 or more degrees of freedom. And since we have laid out the general formalism, that doesn't mean that we are done with classical mechanics and there is nothing more to prove or something like that. We can always have much more details in any of the subject, is what I think. And it's the same with classical mechanics, and researchers and many other things are still going on in the field. So some interesting books that I would like to recommend is the history of classical physics, and most importantly, George Gomo's 30 years that shook physics and the evolution of physics, and the most famous the Feynman lectures, and S. Chandrasekhar's Newton's Principia for the common reader. Yes, this quote from Hawking, and yes, reference. With this, I conclude my talk. I think I shoot by 5-10 minutes, but that's okay. Okay, I think. Okay, thank you. If anyone has any questions or want to say something or want to add something, you're please feel free to do so.
Does anyone have any questions?
All right. If there's no questions, then I'd like to call Shivani to deliver the vote of thanks.
Thank you, Vikrant. So, thank you so much, Amogha, for such an amazing talk. And I know you hope it put a lot of things into perspective, especially for the first years who are doing a course on classical mechanics this semester. And I would also like to thank Parul ma'am and the rest of the department for taking time from their busy schedule and being here to attend the talk. And I just hope to see you all in the upcoming student series seminar talks as well. So I just hope you all had a great time. Thank you. Over to you, Vikrant.
Thank you, Shivani, and thanks, Amoga. It was a great talk. And I think we can end the meeting here. Jalak, you can stop recording.
Yes, yes.
Thank you all for joining in. Thank you. We'll see you all soon.